All right, so it's Wednesday, November 11th, I guess. Yeah. Hi, Svi. Let's see, we have Rose here, we got Bennett, and we got Aya. Okay. The usual suspects. Yeah.
Before we start, is there anything at the school right now that I need to pick up?
Well, there's the take-home test.
Yeah, I got that the day I was there. I think I'll be there tomorrow anyway, but
you know, we're working on stuff. Tomorrow's a good day to come because we're gonna do an activity in the hallway. It might take up a good chunk of the hour. So it's a good day to be there. I mean, I'll videotape it, but it's always better to kind of be involved. It's something you could do at home. We'll talk about it tomorrow, but okay. Anything else before we start sharing screens? Yeah. I've noticed a lot of you come by the porch, which is good. Pick stuff up. The system's working okay. All right.
Are we going to go over those homework questions from yesterday or not? Okay.
Yes, we are. Yeah, that's what we did in class. So let me share the screen, and then when we share the screen, we'll go over the homework. All right, so all right, class number 16, Pkt2. Now the finger dance, I've had two groups come in and do it. Well, one group came in and did it at lunch. One group sent me a video. And I think this is from sheet 2.4, something like that. On the back, there's all those finger dance choreographies you're supposed to do. So for virtual, I think we said 7. I think I made you guys group 7. Yeah, so it's worth up to 25 points. Both groups that have come in and done it so far have given them 25 points each. And I extended that deadline till Sunday after Thanksgiving. So that's like the 29th. And the finger dance, you know, is the thing. You don't have to finger dance. You could actually dance. You could be creative, right? But somehow you got to show that you understand the integral process going from velocity versus time up to position versus time. That's what finger dance does for you. Black and blue, that is due. I noticed I had about 40 views on the YouTube channel. So out of 81, I'll take 40. That's pretty good. And it's not due until tomorrow at 6 o'clock. Okay, so hopefully you've gotten your test off the porch. Now, if you decide not to do it, that's fine. But you've got to get it back to the porch by 6 o'clock tomorrow night, okay, for the credit. There's fairly severe penalty on those for being late. I just don't like my tests out there for very long. All right. So, okay, so today's physics, first hour, second hour, third hour. And we talked about this yesterday. What we're trying to do, the acceleration, if that's x versus t, the acceleration is boiling that down to one number. Boiling the curvature of that function down to one number, and that's really what acceleration is. You can't say it's one slope, but you can say that the slope of the slope, this is the way it's trending. So it's a second derivative, which in finance, you guys ever heard of derivatives in finance? People that do the derivative market, they're looking at. This is Mara Nitzoff, is a old student, and he's become a friend. He's like 40 years old now, but he runs the derivative markets in Chicago. He works for a group called Citadel, and he's in charge of Apple stock for all his clients. And so he does derivatives. Well, derivative is, when you do a derivative of something, you're looking at how it changes. Well, if you do the derivative of the derivative, you look for more long-term forecasts. So he's really good at that kind of stuff. and he's made a lot of money. If you get into the derivative market and you're good, you can easily make $500,000 a year. And so he'll throw me a bone every once in a while, cut me a check for a couple $1,000s and give it to the robotics. He gives it to Norman High Robotics because he was my old leader. But the point is that it's a physics concept, but the point is that you're learning concepts here that'll be applied to finance world or other areas of science too. But this right here, this is the second derivative. And that in this particular case, that's considered to be acceleration. But this line right there tells me a lot about this curve up here. It's hidden, but it is basically this is what dictates this. Okay. Just like in finance world, you go, well, here's the overall trends I'm seeing. So now I'm talking long-term forecast, long-term gains, 6 months from now. That's what people doing derivatives are being paid to do, is look and see what the future is. Not just next week, but 2 months from now. Secant tangents. We came up with those two equations yesterday. Both of these we're going to use starting not tomorrow, but maybe Friday, to derive the 3 orange equations. Okay, first, let's get through all that. I'll minimize the other hours, and here we go. All right, so here's where we ended up, and then the homework. This was what we came up with yesterday. That's the thing you've got to memorize, but memorize the patterns. It's like I said yesterday. I mean, if you're trying to count to 100, you don't say 72, 98, 14. You don't do that. You put them in order. And the same thing here. If you do this as a pattern, it's not that hard to remember. So we have questions that I asked individuals and groups in class to answer these questions. So let's run through these real quick, 1 through 9. This is that I'm instituting this thing called a 10-minute homework assignment, 10 to 15 minutes. And that means that you don't have to be perfect on it. It's just I want you to familiarize yourself with it, so that when we go over it, you've given it a shot. Okay. So number 1, a solo graph represents an object which is, and that's fairly obvious, it's sitting still, right? Stationary or sitting still. Just say stationary. Static. Static is the term. I didn't use that in class, but that's the term we use for objects that aren't moving. They are static. Okay. You can have an object that's not accelerating, it's not static. It can be in what's called, I think maybe in chemistry, you learned a concept called equilibrium. Did you learn equilibrium in chemistry? Or maybe you haven't had chemistry. No? Anybody had chemistry? Anybody learn a concept called dynamic equilibrium? Where everything's in stasis? Okay, everything's in dynamic equilibrium, everything's in stasis. It's all like a liquid into gas going back and forth. That's called equilibrium, but that's dynamic equilibrium. This is static equilibrium, meaning that all forces cancel and there's no motion. That's a situation where you have a solo graph for position. Number 2, what is the acceleration of an object whose motion is represented by a duet? And what say you? What's going on here? What's the acceleration of this object? I got a small class, so I only got 4 of you. Start calling.
In a positive direction.
It's well, I agree it's going in a positive direction, but what's the acceleration?
Wouldn't the acceleration be constant since it's not speeding
Now,
up?
if it's worth 10 points and you wrote down constant, you would get a 6 out of 10. Why not 10 out of 10? In a trio situation, that's constant acceleration, right? It's constant. In a trio, that acceleration is not changing. But what about in a duet? What's the acceleration?
No acceleration?
There is no acceleration. You can be specific, right? So if you said constant, I'm not saying you're wrong, just that you can be more specific. More specific would be 0. So acceleration is 0 in a duet. So 0. Okay. List the graphs above by number, which represent a positive constant acceleration. Well, let's go to rows. Which one is a positive constant acceleration?
Number 6 or
Oh,
graph 6.
Rose, you changed. All right,
Oh.
so Io, that's all right, Io, you jumped in there. Rose, you want to add anything to that? He said, I'm not disagreeing with Io. He said 6. He said 6 represents constant positive acceleration. I'm not arguing with that. Is there any more?
Would 9 be one?
9, it's constantly increasing. So 9 is a situation of constant jerk. But if I say, okay, so this is the Rosetta Stone of motion. We gave the analogy in class of the periodic table. And Mendeleev, the Russian, started to develop the periodic table in the 1800s. I don't know, 1850, somewhere 1870, somewhere in there. It's been a while since I taught chemistry. But he didn't know jack squat about the atom. He didn't know what an electron was. J.J. Thomson didn't discover the electron until 1897. We didn't discover the nucleus till 1911, Rutherford. So Mendeleev, but started to put elements like metals and stuff. He put them in columns. I don't know why, but it stuck. So those columns are families of the periodic table. So all the alkali metals react the same way. All the halogens react the same way, right? So, and alkali earth metals react the same way. It's because of electrons. We didn't know that though. So it's the same thing here. If it's called a family. These are families. All right. So if it's true for one member of the family, it's true for all the members of the family. This acceleration is grandpa. Okay. Acceleration begets velocity, which gives us position. So you can go from the top down. We said that's called slopes. You can go from the bottom up, which is called area. We've been going from the top down, but we're going to start going here more next semester when we get into energy and work. We're going to start going from the bottom up. Okay, and that's called integration. All right, finger dance stuff. Okay. My point is, if it's true for 6, if it's true for acceleration, it's also true for 4 and 5. All 3 of those. So it's a family thing. So 3 says, list the graphs above. So that would be 4, 5, 6. All of them in that family, in the trio family. Okay. Now we're catching on. 4, list the graphs above, which represent displacement increasing parabolically with time. And I'll open this to anybody. Who wants to answer that? Displacement increasing parabolically with time.
Wouldn't that also be 4, 5, and 6?
Right, it's that same family. If it's constant acceleration, then displacement is increasing parabolically with time, 4, 5, and 6. 5 says, list the graphs above which represent velocity increasing parabolically with time. And what family are we talking about now?
The quartet family.
Right, so now we're talking about 7, 8, 9, 10. So that's the idea here. That's a concept once you get it, these families of motion. And once you get good at it, you start to see things happening. Like I see a car speeding down the road or speeding up, and I'm thinking, what's that? X versus T, V versus T, A versus T. It gets in your head eventually. You start to see the world through graphs. 7 says, briefly describe the movement of an object represented by a duet set of graphs. Well, I'll do that. I'll do that one. I mean, it's pretty easy. For a duet, the object is moving at a constant velocity, right? I'm walking to class, I'm jogging. It's a constant velocity. Now, velocity here, be careful, because someone said, well, it's somebody like velocity, jogging on a track. like at the Harv, you know, but that's not really true. Why wouldn't this, they're jogging at a constant speed. Why wouldn't this graph, why wouldn't this pair, the duet, tell me what's going on there?
Because you'll slow down or speed up whenever you reach like the curves of the track.
Let's assume I'm not going to speed up. I'm going to go at 4 meters a second.
The
Still
direction.
the direction, right? So even though I'm not speeding up or slowing down, if I change direction, that changes velocity, because velocity is a vector. So this only works for things that are going in one direction. Okay. Just had to be a jerk about it. Not a jerk. It's a duet. So briefly, so that's moving in one direction at a constant velocity. V equals K. One direction, like the band. 8, briefly describe the movement of an object represented by a trio. And Bennett, what do you think about that one? A trio. What's the object doing there?
It accelerates from a stop to whatever the final velocity is steadily.
And it accelerates at a constant rate, right? Okay, so that's like a ball rolling down a ramp. Okay, it's speeding. The light turns green. You hit the gas. You slowly speed up, and at the end of 30 seconds, you're going 30 miles an hour. So that would be an example of a trio. Something speeding up. If it's a positive trio, in the positive direction, speeding up in the positive direction at a constant acceleration. And finally, we get to what is a quartet? What's going on in a quartet? Now, this is something we haven't talked about yet, but this is called thrust. Now, in class, I held up a rocket, and I talked about we do rocketry. Now, you all, if you're juniors or sophomores, you all will have the opportunity next year to come by the room on Tuesdays at lunch, and learn from the best rocket, the best model rocket guy in this part of the country. His name is Mike Babb, and he is an aerospace engineer with Tinker Air Force Base. He goes in, and if any kind of F-15 crashes in the world, he has to go find out why they crashed. So he does CSI on Air Force crashes. He's got some horrific stories he doesn't tell you guys, but sometimes these pilots punch out and they don't, like the canopy doesn't open or something. I mean, there's all these horror stories. But he knows aerospace. He's a fan of the space industry. So that'll be on Tuesdays if he agrees to do it one more time next year. But we come up with something called the thrust equation. And I'll just throw it out there. It's F equals m dot VE. Now that means nothing to you. I didn't tell the classes this today. That means nothing to you right now, but we will talk about it. And that is next semester. And this is when a rocket, while the engines are firing, it can also be an F-15 while the rockets are firing, right? That's called thrust. It's a whole thing. But that's an example of jerk. We talked about our model rockets. They're about 4 feet high. They go about 4,000 feet up there. They take off supersonically. They have G motors, which is a pretty big motor. Okay. And then we talked about Apollo, the Apollo series of NASA, and Apollo series the later Apollo missions used Saturn V rocket. And there's a model of a Saturn V rocket hanging from my ceiling in the room. So we went through and talked about the stages. And we talked about Neil Armstrong and Buzz Aldrin and how they're up there. So we talked about who developed the Saturn V. Saturn V is the biggest rocket ever built by man. It's the most powerful rocket ever built by man. the engineer that put it together was called a guy named Werner von Braun. And Werner von Braun was a Nazi. He was part of the Nazi. He was with Hitler. He was in charge of rockets. Germans are really good at rockets. And so because of the Treaty of Versailles, they couldn't do a lot of things, but they could. We didn't mention rockets. And so they put all their research into rockets. And they developed the V2 rocket. They terrorized London, little World War II history. But Werner von Braun was the head of that group. And him and his scientists, as we were taking over, they hid in a cave. And we were the Americans were the first ones to get to him. Thank goodness, not the Russians. And we captured him. They gave themselves up. And Werner von Braun and his team became these Nazis. And I'm not a QAnon guy. I'm not a QAnon guy, man. This is not, I'm not giving you conspiracy theories, okay? This is known history. They just don't talk about it much in the history books because it's not, it's not patriotic American, but yeah, so really our space program was started by a group of ex-Nazis. Anyway, there's a whole story. That's a whole crazy story, man. If you look into it, look up Werner von Braun, look up Wikipedia. That's quite hair-raising. He's a genius, the guy was. But anyway, so the point I'm making with all that is he and others developed, well, a guy named Stravinsky, another guy, a Russian guy, or Tchaikovsky, came up with thrust equation. And so this is what we're going to study pretty heavily next semester. But the motion involved in a rocket, and like Neil Armstrong and Buzz Aldrin, when they're sitting on top of that candle, as they say, a huge Saturn V, they experienced a jerk, a quartet, because as the engines are firing, you are being thrust. All right, so it's called thrust. Okay. So that answers those questions. Okay. Now, 10 and 11, we didn't do in class. I told them that I said that that's homework for you guys, but I said that I would answer it now. So 10 and 11, take a look here. I said I'd answer it in the wrap-up video. But 10's not hard. It says, when we roll the steel ball down the ramp, down that tube, how did the distance covered by the ball change as time increased? And how would you answer that? How did the distance change as time increased? So looking at your graphs, how is the distance changing as time's increasing if a ball is rolling down a ramp?
Wouldn't distance just be increasing? Or
It is,
that
but
technical?
isn't that the case? Isn't that the case here? Isn't distance increasing with time?
Yeah.
Well, this is something different, right? This is not, the ball was not rolling at a constant velocity. So good start. Let's keep going. What's the ball doing as it rolls down the ramp?
Speeding up.
So now distance is, and students always want to say, and they say this on tests, on this question, they say that the distance is growing exponentially with time. Is that a false statement? Nope, that's not false. But if you tell me that the distance is growing exponentially with time, my question to you is, which one of these two is it? They're both growing exponentially with time. Now what say you? Ball rolling down a ramp. How does the distance change with time? Saying it increases is not good enough. Saying it increases exponentially is better. Okay, here we go. Scoring a test. A student says the distance increases with time, and it's worth 10 points. I give them a 3 out of 10 for that. A student says distance is increasing exponentially with time. I give them a 6 out of 10 for that. You got to be more specific. How is the distance increasing with time? I mean, that ball is not thrusting, doesn't have a rocket attached to it. So it's not going up. It's not going up, cubically.
Would you just say it's accelerating, or?
It is accelerating, but it's asking you, how is the distance changing with time? How is x changing with t? In other words, describe that curve. Give me a word for that curve. Exponentially.
Constant.
That curve. Oh, the curve. The curve of the curve is changing. The slope of the curve is changing constantly. I'll give you that. But what is the name of that curve?
Parabola.
Parabola.
There's the zoom point. Parabolically. So if you answered parabolically in a test, that's 10 out of 10. Parabolically. So you guys are my guinea pigs here. I go over, I talk to you guys on this, and now I know what the classes tomorrow are going to ask. And what they're going to say. Sometimes they're ahead of you, sometimes you're ahead of them. Okay, so you got to say something about, well, the distance covered, which set of graphs represents motion, and that's the trio, and the distance is changing parabolically with time, is what I'm trying to say. Now 11 is worth looking at. 11 is kind of a review, but now we have an actual function here. Okay, x equals 1/4 t squared. So, we were saying x equals kt squared. So I'm going to turn this heat off. It's getting hot up here. X equals kt squared. But now I'm telling you k is 1/4. So on this one, it says draw that graph right there. This graph is x equals 1/4 t squared. Because when I'm at 8 squared is 64, and 1/4 of 64 is 16. So, okay. So now we answer a series of questions here. Draw the line on the graph below, and I know this was on homework for you, so I know that you haven't looked at this yet. It says draw the line on the graph below, which has a slope. You need a straight edge for this, which has a slope equal to the average velocity. So get out your rulers, and that, as we know, average means secant. And so just draw. This is a little bit of review, but it's okay. Always good to review some. So this is the official key. So I got to make this look good. I'm not going to have time tomorrow to talk about this in class. I think I'm really starting to worry that we're not getting very far. We're making good progress, but we're still, and I've cut corners, and we're still 3 weeks behind last year. The 4 snow days didn't help. All right, so what is the mathematical? So we drew that line. It says, what's the mathematical name of this type? We already called a secant, so that's a secant line. Secant lines turn hit curves in 2 points. What does its slope represent? And we know that secant slope. What would you say? You tell me. What does secant slope represent?
So wouldn't it be 16 meters over 8 seconds?
Yeah, okay, I'll go with that. So the actual number is 16 meters over 8 seconds, or 2 meters per second, right? So the secant slope is 2 meters per second. Might as well put that in there. 2 meters per second. But what does that represent? Is that the velocity of the curve?
The overall average.
Right. So that represents. Thank you. So there's the point. So that's the overall average. That's the V bar. It represents V bar. Okay, C, draw two lines on the graph below representing the instantaneous velocities of the object at 0 meters and 16 meters. Now I've adapted green to be tangent, so and orange to be average. So the green line here, the initial tangent line, is flat to begin with. Remember, the tangent line is telling you it's kissing the curve, and it's telling you the slope of that curve at that instant. Okay, cool. All right, so hold on, I'm just talking to myself. So 1 over and 4, 1 over 4 up. Okay. 1 over 4 up. I know from calculus what it's supposed to be. That's right. This is exactly it. If you know calculus, anybody here in calculus? Calculus gives you an advantage here. Calculus always gives you shortcuts. So that's I'm positive. That is, I'm kissing that curve at the end. So that's the green at the end. That's the velocity. So this represents V naught, the slope of this. The slope of this represents V final. What is the mathematical name of these? Okay, these are tangent lines. What do their slopes represent? Instantaneous velocity, not average, instantaneous. You say, Mr. Ask, you sure have an obsession with average and instantaneous? Well, I do because Isaac Newton did. And the name of this course is classical physics. It's classical physics mechanics, which means we study the foundations of movement and we study what causes that. We'll eventually get to forces because forces is what causes acceleration. And then we'll get to masses because masses is what's being accelerated. History of physics, right? You can trace it back to the history of gravity. There ought to be a book, there probably is a book, called The History of Gravity, because that's what started physics, is trying to understand gravity. Da Vinci jumps off the Leaning Tower, right? He considers it, he fantasizes about it, about flying, and they considering gravity in 1495. Galileo studies it. I mean, other Kepler, people studied it in astronomy. Galileo studied it on Earth, rolling balls down ramps. He's studying gravity. Newton came up with the Law of Universal Gravitation. That's one of the top 5 equations. We haven't got to it yet, but we will. Einstein studied gravity. And so and then what's the Large Hadron Collider doing? Studying mass, studying the Higgs boson, which is basically the basis of all mass. Where does mass come from? But if you have mass, therefore you have gravity. Okay, so you can trace physics from basically it's thinking about gravity for the last 500 years, and we still don't get it. We're closer. So if you want to spend your entire life studying something you're never going to fully understand, study gravity. Maybe you'll make the breakthrough. The cool thing is they give you Nobel Prize. All right, so E, what is the mathematical relationship of the slopes of the, can you tell me? I'll give you 3 Zoom points if you can tell me this equation.
Is it the V naught plus VF over 2?
Oh, you got it. That's right. I thought it was going to be harder than that. 3 points to you. V bar equals V naught plus V final divided by 2. Oh my goodness, we got to go over this one tomorrow. Okay, this is big. I forgot this is such a big problem. So would you agree that the secant slope is 2 meters a second? We all showed that. That is the average. So, oh man, it's going to be good tomorrow. 2 meters per second is that. V naught, you agree that V naught is flat. V naught is 0, right? okay, 0. V final, we're trying to solve for V final, instantaneous velocity. Well, multiply by 2, and V final equals 4 meters a second. This is a trick that Newton used, because if you start that means if you start a ball rolling down a ramp, and you can measure the average velocity of that ball. You know the length of the ramp. You can determine the total time. Remember that V bar also equals delta X total over tau. So if I can just measure the entire time, I know how long the ramp is. All I do is double it, and I know the velocity of the ball at the bottom of the ramp, the instantaneous velocity. And that's what we want, instantaneous velocity, not average. Okay. Whew, 41 minutes, we gotta keep moving. If we do 12 and 13, then I'll be happy, okay? Let's knock off 12 and 13. Now, 12 and 13, a reminder here, the test next week covers 2.1 through 2.7. It does not cover this sheet. Now, this sheet will be covered after Thanksgiving, maybe in a quiz, but it'll be on the final. I might throw a quiz in there December 10th or something, but it won't be like a piece of paper and you got to come get it. And well, that won't happen. I'm going to, for next Friday, I'm going to send you a PDF. Okay. I'll put a PDF up for the test. So you don't have to come, you can print off your own. Now I'll have paper copies in the porch if you need them, but, and then you'll take it and then you'll take a picture of it, you send it back to me. Okay. That way we don't do this whole paper thing for next Friday. Okay.
Will our notes be due too then,
No,
or
no,
for the final?
no, yes, for the final. In fact, I'm glad you said that, because those final notes are worth already 100 points. They're going to be worth 100 points. The last set of notes are only worth 34 points, but these are going to be, there's going to be more I expect more notes. So I expect about 3 times the amount. Now we're not there yet. This is like, December 18th or 19th, but I expect 3 times the notes that I got in packet 1 to have 100 points. So keep that in mind. But remember, notes, quote, notes could be you just working on problems. It could be you writing a physics haiku. I mean, it can be anything involving physics where you're pondering physics. Maybe you read it, maybe you watch YouTube and you write some notes about it. That would be good. I'm happy with that. That's notes. Okay. So I'm happy for you to be creative on your notes. Okay. Anyway, and you can get up, and it's worth 100 points, but you can get up to 120 out of 100. You can get 20 points bonus on those notes if you put in some really good work. Now, not everybody's gonna get that. So a few people will. Okay, let's knock off 12 and 13. 12 said if K, the constant, is 4 meters per second squared, in the equation for a positive V versus T graph, when acceleration is constant, boom, which family am I in if acceleration is constant over here? Which family is this?
Trio.
That's trio. So now I know, and I'm talking about V versus T. So now I know which graph I'm working with. I'm working with this one right here. Okay, that helps. So now I know I'm dealing with a linear graph. So I can go ahead and sketch that out. In fact, when you see this on a test, I ask you to sketch it out too. So V versus T, I know, is linear. It's with a slope. Okay, and I know that the constant, well, the equation for that is, I'm telling you, man, that Rosetta Stone, that really helps. It's like a table of contents of motion. You can always go back to it and kind of say, okay, where am I? Where am I? I'm in the trio. All right. So V equals 4. Well, hold it. Get ahead of myself. V equals AT plus V naught. Now, that's the equation, right, for that for a trio in velocity. Well, how do I know that this 4 is acceleration? Didn't say it was.
It's meters per second squared.
Because of its units, right? So now let's talk about this for a second. This came up in class. Meters per second is what a purist would say acceleration is. It's really meters per second. Now dig this. Okay. Hold on. A student a few years back said in class, he said, that's okay. It doesn't, he said, I was thinking about this last night, and I was using meters per second, and sometimes I'd use meters per second squared. And he says, how can you say they're the same thing? He was a very smart student. He says, you're telling me meters per second, that's division, and you're saying that that's the same thing as multiplication? Does that bother anybody else? Isn't that weird? Doesn't seem right. Okay. So that's when I started doing this. I said, okay. Yes, that's not true. No, but it's meters per second. This is a little per. That's a big per. Meters per second. So so watch. If that's the case, I have meters per second. I can multiply this by a clever form of 1. You can multiply anything by 1. And I'm going to choose seconds over 1 over seconds over 1. Okay. When I do that, my little green kill pin comes out. The seconds die there on top. And that just becomes meters. And on bottom, seconds get multiplied together, it becomes seconds squared. Okay. So that's why a purist would say meters per second, but a mathematician would just say meters per second squared if they use any units at all. And then I'll leave this to you if you want to try it. Meters per second equals meters per second cubed, like a jerk, right? Well, explain that one. Show me, don't do it now, but if you're in your notes, right? In your notes, if you want to, start getting some little note space up, start messing with that. And that reminds me, I'm gonna back off this. I totally forgot to do something with you. That's why we're so far. I knew we're missing something. I made them go to the board on your back on the front of 2.8. I made them go to the board and draw a quintet. I said, okay, it's 5 graphs. Now draw me a quintet. Draw a quintet. And you have a little tiny bit of sliver of space over there. If you want to squeeze it in to the right in the margin, you can do that. Or hey, on your notes, right? Maximize your notes. Just always date your notes. Put 11/11, and then just put 11/11, put a line, and then just write stuff down so that you can go back and remember what you were talking about. Because you're not going to be tested over this till possibly mid-December, a month from now. Okay, so I'm going to give you a minute to come up with the graphs, the equation, the units, the symbols, the order, all that using your pattern. The beautiful patterns. Okay, so this is you going to the board. And usually while they do that, I drink my coffee. No coffee. So while you're going to the board, I'll look at my phone. Teachers have all these group meetings that we're in. Teachers complain about everything. You know, the one thing they don't complain about? Students. I've never heard a teacher say something bad about a student. Because if they do, the rest of us would pounce on them. You know, we say plenty of bad stuff about administrators, and sometimes not such nice stuff about parents, but we never say anything bad about students because you're the reason we're there. So I was just reading this, and they're all going on and on about how they like this person. It's good. Teaching is a good profession. Okay, keep going, and I'm going to start working on it too. I start at the bottom and I work my way up, right? Start at the foundation. You always know it's going to be flat. You can't go below flat. Someone asked that once. Well, what's below a jerk? You can't keep, once you've gone flat, there is no slope. Flat has no slope. So that's all you can do. Okay. This is one to take a picture of. One look nice. Get the T's out of the way. It's all T. So I bet you have a question. What question you got? Because this is showing us something we haven't talked about yet. The new guy.
Why don't you use like a cubic function?
Oh, because there's okay. I'm giving you 2 points for that because I'm just daydreaming here. 2 points for that. If that thing had got through, I would have destroyed the whole tape. 3 points for that. That's pretty huge. I would have caught it, maybe. All right, so that's X. That's V. The slope of V is A. The slope of A is jerk. But what's the slope of jerk?
I looked it up and saw something called snap.
Ah, snap. I'm there. That's pretty good. You looked it up. I'm going to give you a couple points on that one. Snap. You guys are racking in the Zoom points today. Snap. You know, snap. Hey, IO, where you found that didn't give you a symbol for it though. Because I've never seen a symbol for snap. You can't use S because S is a generalized position, or generalized, like delta S is generalized displacement. So I use SN. I don't like it, but I don't know what else to call it. So it's just, thing is, it's not, this is sort of academic exercise. If there's a snap involved, you're probably dead. Nah, you're in the hospital. Okay. Hey, what's below snap? What's the slope of snap? If we were to go to a sextet, what's the slope of snap?
I saw crackle.
It's something called crackle. Well, it begs the question, what's the slope of crackle?
Pop.
Pop. Snap, crackle, pop. See, physicists have a sense of humor. Daggone it. Snap, crackle, pop. A little whimsical, but it's a pretty good descriptor because snap, jerk is going to jerk. You're going to have whiplash, right? Snap's going to break a bone. Crackle's going to crack your spine. Pop's going to, I don't know, blow up or something. You're not going to survive a snap. All right, so this is, now we go to that. We go, all right, this is, blow this up a little bit. This is meters per second. I'm gonna be lazy. Meters per second squared. Meters per second, or meters per second cubed. And meters per second. Meters per second to the fourth. Oops. We do talk about snap a little bit and crackle occasionally. You'll see when. Really complicated motion. Oops, wrong. Second to the fourth. Okay. And equations. So we have, snap.
Snap would equal snap not.
Snap not. And then, et cetera. So then jerk, now we get to the whole thing. That equals snap times t plus jerk not. These names get funny. Now acceleration, we just go ahead and say acceleration is kt squared. Now this k keeps changing, so it's just a generalized k. V now is changing as the cube of time, kt cubed. And then x equals kt to the fourth. So a fourth, something to the fourth power looks like a very skinny parabola. All right, so good. So now you guys have gone to the board. Now let's go pick this up then. Let's finish this up then. So if we're back on number 12, therefore we know acceleration is 4. So our equation in V naught, you have to assume that V naught is equal to 0. And it doesn't tell you it's not, you have to assume it is. So V then equals 4 meters per second squared times t. Well, it says what's the velocity change between the third and fourth second? All right, so, and you got to graph it out. So, I promise we're almost done. Third, fourth, that's some kind of V, and that's some kind of V. Well, what is V when t is equal to 3? You guys still there? What's V? 12. And then what is V when t equals 4?
16.
So the delta V is 4 meters per second, just meters per second. Because, well, that's obvious. The slope is 4. So what would it be between the third and fifth second? How much speed would increase?
Would it increase by 8?
8. And then what about between the third and the sixth second?
12.
12, right? So we're looking at a ball rolling down a pretty steep ramp. That's all. Hey, here's a question. This is just for you guys. What would be? That's if a ball is rolling down a ramp, right? 4 meters per second. What if the ramp was 90 degrees and the ball was falling? Now, how fast is it going to roll? Or let's say it's 89 degrees and the ball's barely even attached, but it's still like El Capitan Reef. It's still rolling. The ultimate speed on Earth is
Gravity.
And what is that acceleration?
9.81.
There you go. So I'm giving you a point for gravity and a point for 9.81 meters per second squared. We're going to test that ourselves at the Harv later on. It'll probably be a cold day. Finally, last question. Now let's kick it up a notch. K is 6 meters per second cubed. So what is that? What, by those units, what is that thing?
Quad family.
It is the quartet. So this must be jerk, right? That's jerk because it's constant, a jerk of 6, which is really high. Remember we said yesterday that subways aren't supposed to have a jerk over 2. This is a jerk of 6. This would hurt really bad. Okay, so in the equation for a positive x versus t graph, well, if that's the case, jerk is constant. And so my x versus t graph is cubic, boom, 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 boom. How much will the position change between the 4th and the 5th second? So I want to know what would be my delta x. Blow it up a little bit. Delta x between, this is x versus t, the delta x between the 4th and 5th second, if the jerk of that curve is 6 meters per second cubed. We already said, I made a mistake. That's not true. The jerk is there, but it's not 6. The K is 6. You'll see why. It's a calculus thing. So jerk, no. This is what happens when I get in a hurry. X then equals 6 meters per second cubed. When our time gets over an hour, I get really nervous. I'm sorry. I know I'm going along today. Almost done. 6 meters per second cubed, t cubed, right? That's our equation. And so all we got to do is take x of 5, subtract from that x of 4, and we have our answer. X of 5 then is 6 meters per second cubed times 5 seconds cubed. And then x of 4 is 6 meters per second cubed times 4 seconds cubed. Okay. Well, 5 cubes, 125. So it's 125 times 6 is 750. So 750 meters minus 4 cubed is 64 times 6 is 384, right? 384. Somebody double check that. 384 is 64 times 6, 384.
Yeah, you're right.
Okay. We subtract those two and we get 366 meters. Well, let's put this in. This is physics, right? So we're supposed to understand things. So we put this 366 in perspective. That means between the 4th and 5th second, if this is thrust, if you're being thrusted and you're being thrusted for a long time, you are now going in 1 second, you're going 4 football fields almost. Your body's going 4. No human's going to handle this. You're going to be dead, right? The Apollo, the Saturn V, put Neil Armstrong and those guys in a thrust situation, but the jerk was not 6. If you have a ludicrous mode in a Tesla, you can punch that button and you may get to a jerk of 3 or 4. I don't think you get to 6 though. It wouldn't last long. You'd be at 100 miles an hour in no time. So last thing, since we're talking about Tesla and Elon Musk, yesterday, the first 2 humans, they put them in a Hyperloop and they sent it, they took off. Now a Hyperloop, we had a question on that earlier on this year. Eventually there'll be a Hyperloop between Oklahoma City, or between Norman, Oklahoma City, and Dallas. And it's estimated to be about 18 minutes. It'll take you 18 minutes to get from Norman to Dallas in a Hyperloop. So they're in a vacuum tube. You're strapped in, but the hardest part is accelerating you because you're experiencing G-forces. Once you get to your travel speed, you don't even know it. You won't even feel it. But accelerating you and then negatively accelerating you once you get to Dallas. But the actual not flying, but the actual tube is once you go to constant speed. So they put 2 people in one. They put the engineer and they put the person who's marketing it for a company, and they did a big thing on it yesterday. You should look it up on YouTube. People in Hyperloop. Do a recent search. So that's kind of cool that's coming to fruition, which means that in your lifetime, you'll ride a Hyperloop. I don't know if I ever will, but you will ride a Hyperloop, maybe to Dallas. they'll start in LA. They're talking about LA to San Francisco, LA to San Diego. They're in Dubai right now. They're working on them in Dubai as well. Okay. I guess I can stop the sharing. So I guess we went way over today. I apologize profusely. But it was a good session. We learned a lot. All right. Tomorrow won't be as long, I promise you. We'll be doing lab in class. So I'll show you a video of it here of what we did. Okay. Any questions? You know, tomorrow your black and blues due. Next Tuesday, your take-home test is due. And we did the homework here. So that's the other thing. At least there's no other homework for you. Okay, y'all, you're becoming really good physicists here. So I'll see you guys tomorrow for our last meeting this week. Bye-bye.